Oh no, there's this thing in the middle. Oh, good, good, good. Hello? Hello, can people at home hear me? Can the people over Zoom hear me? Yen Hong, can you hear me? Chen Nan, can you hear me? No? Hello, can you hear me? Okay, good, good. Okay, 2 more minutes. Okay. We still have a lot of people who like to attend in person, which is really good. Okay, I'm very far away from all of you, so I think I can remote us. Very difficult to talk. Enough distance, right? That is very difficult. This is chapter 4. Today's reading, I don't know, it's at the start of chapter 4. So you read until we talk about period of Markov chain. I don't know what that section is, but we are going to cover up to the notion of period. Okay. Oh, one person here. This is a bit cumbersome. Can we just not let everybody come in without having to approve? Some setting. Okay, so I guess everybody is okay now, settled. People at home people in the Zoom can hear me? Just to confirm, good. All right. Okay, so today we will start a new topic. And this topic is Markov chains. Markov chains is very important. It's a very important area of study in stochastic processes, because up to now, we have probably been just dealing with IID random variables. Okay, we talked about IID random variables when we talked about large deviations and some sort of concentration bounds like Chebyshev's inequality and Chernoff bound and so on. And we talk about IID inter-arrival times when we discuss Poisson processes. But when we want to talk about general stochastic processes, really there are only three other major topics that typically stochastic processes courses would cover. All right, one would definitely talk about Poisson processes. One would definitely talk about Markov chains. One would talk about martingales in a stochastic process 2 course, and one would talk about Brownian motion. All right, so these are the fundamental stochastic processes people will study. Martingales, I gave you a problem on it, but we won't really delve too much into it in this course. And of course, Brownian motion is a bit complicated, though it's really beautiful. Okay, so we'll spend 3 full weeks on Markov chains. Maybe not 3 full weeks, because next week there's a quiz. I will send out details about the quiz very, very soon. Okay, but essentially it's just the same as last time. Okay, except that last time you all started the quiz at 8 o'clock, right? So I got some requests to say, oh, we should start it at the beginning, 6 o'clock. All right, so yeah, I'm very nice. So we will start it at 6 and we'll end at 7. And this time, last time the total was 40 marks, right? So this time the maximum is 25 marks. So we will really do it in 1 hour. There's no extension whatsoever, because the quiz is indeed shorter. Okay, so there are fewer questions, and I think it's significantly easier, because I don't want people to get too upset, right? So yeah, that's the quiz. It will start at 6 o'clock next week. I got some requests for it starting at 6 o'clock, so you're more fresh. Okay. All right. So Markov chains is a canonical type of sequence of random variables that is not IID. We don't just want to deal with IID random variables. So, and in particular, we will only have time to talk about finite state Markov chains. That is the topic of chapter 4. So here we are considering a sequence of random variables such that each random variable xn takes on values in S. And S is a finite set. Each xn takes on values in a finite set. So we can say that it has finite support. All right. Or rather, xn is a discrete random variable. Okay. Some people say that discrete random variable can also take on countable number of states, but let's just be on the same page that this is a discrete random variable, take on only finitely many possibilities. All right. So we will consider this sequence of random variables xn, where n is can be thought of as discrete time. So as I mentioned at the very beginning, a stochastic process is nothing but a sequence of random variables. And this is the sequence of random variables that we are dealing with. This is our stochastic process. But if this whole process has got no structure whatsoever, then there's no hope of us studying any interesting properties about it, right? So we want to be able to study the behavior of this stochastic process or object in a meaningful way, all right? So we want to define the notion of a Markov chain. Actually, this Markov chain is a discrete time Markov chain. So let's make that clear. There are things known as continuous time Markov chain. A discrete time Markov chain, xn, okay? Actually, n can start from 0 or 1. Sometimes we start from 0. Say, let's be consistent. Okay, sometimes I write this, sometimes I write this. They mean the same thing, okay? We're not going to be too pedantic about such things. Is an integer time stochastic process. So this is not too unlike our sequence of inter-arrivals, but our sequence of inter-arrivals is also indexed by discrete time, okay? However, those are IID, but these are not going to be IID. For which the defining property is that xn depends on its most recent random variable xn minus 1. Okay, so mathematically, so this is the definition of discrete time Markov chain, a very important definition. And we'll be studying its properties for the next 3 weeks, okay? So mathematically, what this is saying is that the following. For every n bigger than 1, and for every sequence of states I, j, k belonging to S, so that's the state space, the probability that xn it takes on a certain value j, conditioned on xn minus 1 taking on the value I, xn minus 2 taking on some other value k, all the way up to x0 taking on the value L. Let me have more of these. L in the state space. This is only equal to probability that xn is equal to j conditioned on xn minus 1 equals to I. So it does not really matter. It does not really matter what happened here. All right. It does not really matter what evolved from time 0 to time n minus 2. If I'm interested in xn, all I have to look at is xn minus 1. So what is a real life example of a Markov chain? Okay, so let me just, before I talk about that, okay, for all conditioning events, xn minus 2 equal to k, all the way up to x0 equals to L, okay? So all the I, J, K, L, they are all states in the state space. And here we are conditioning on this arbitrary sequence of events here, okay? And no matter what we condition on, basically this part here is independent of this part here. Now, so this is the formal definition of a Markov chain. It's just this sequence of random variables that has this property that xn is only dependent on its most recent past. It is not dependent on everything else. So I want to give you an example before I talk about the next concept. So what is a very easy to understand example of a Markov chain? So I like to give this example, but I don't know whether it's completely appropriate or not. All right. So we usually like to denote a Markov chain as follows. So this is x0, x1, x2, xn minus 1, and xn. So xn only depends. It's called Bayesian network if you wish. In statistical inference, it's called Bayesian network. Xn only depends on its ancestor. The ancestor is xn minus 1. Okay. So what I like to talk about, the example I like to give is the following. Okay. So suppose I'm interested, I'm a doctor. All right. And I'm interested to find out, to assess your health at age n. Okay, I'm interested to assess your health at age n. All right, so I typically like to ask you, oh, last year, what was your health status? Were you healthy? Were you unhealthy? Did you have this sickness? Do you have that sickness? Then that gives me a pretty good idea about what is your health when you are age n. Now, if you were unhealthy at age n minus 1, I would guess that you'll probably be unhealthy at age n. If you're healthy at age n minus 1, that's here, then you're probably healthy at age n. All right, so as a doctor, I probably don't have to ask you about your entire history. All right, perhaps what is most relevant to me and all the information that is contained in your health history is actually contained in year n minus 1 if we operate in discrete time. So this is health at age n. And your health at age n minus 1 gives a pretty good idea about your health at age n. And I do not need to know the rest to best predict your health at age n. All I need to know is your health at age n minus 1. So that is the way, that's a bit naive. Of course, in real life, you might want to know a patient's health ever since he was born. But if you cannot, then actually his health at age n minus 1 is a pretty good summary of his health at age n. Okay, I know I'm stretching this, but this is one example of a Markov chain. Okay. All right. So this notion here, this quantity here, still depends on n. So we would like to make one more small definition of a homogeneous Markov chain. Okay, so a homogeneous Markov chain is a Markov chain. Okay, it's definitely a Markov chain, otherwise we don't call it a Markov chain. A homogeneous Markov chain is one in which this quantity here, this is called the transition probability. Later on, we'll use the notion. In which this guy here does not depend on n. Only depends on I and j. The states I and j. Okay. So what does this imply? So suppose your Markov, your health status is healthy, unhealthy. There are only two states. Okay. I don't care whether you have cancer or not. You're either healthy or unhealthy. So the chance that you go from healthy to unhealthy is the same regardless of which year you are at. That's the notion of a Markov chain. So here you are a baby of age 1. Okay, here you are age 2. The chance that you were initially healthy and then you became unhealthy is a certain probability. That same probability is the probability that you transition from healthy to unhealthy from age n minus 1 to age n. So this transition or this transition probability does not depend on where you evaluate the Markov chain. So that is called homogeneous Markov chain. Okay, so that's another definition. Okay, so this quantity, this transition probability does not depend on n. All right. So we actually give this a name. So it makes sense now to call this Pij. Pij is nothing but the probability that I end up in state j, whereas I started in state I. And this is, you see the left-hand side here, the left-hand side quantity, I didn't index it by n because from now on, all Markov chains are homogeneous Markov chains. We only deal with homogeneous Markov chains from now on. So the transition does not depend on n. So I don't need to talk about n on the left-hand side. Okay, so this holds for all n and all ij, which I will not write down. Okay, so this is the notion of homogeneous Markov chain. All right, so our Markov chain needs to start from some state, which usually we call x0, initial state of the Markov chain, and x0 has an arbitrary probability distribution over S, over the state space. Okay, so if I tell you the initial probability distribution and I tell you all the Pijs, then I specify the entire Markov chain. This will become apparent very shortly. Okay, maybe what I'm saying now is a bit too fast, but if I tell you what is the initial state and I tell you all these Pijs, which is equivalent to a matrix, all right, then I specify the entire evolution of this stochastic process. Okay, and just as a reminder, S here is our state space, okay, and we will only talk about finite state Markov chains, always finite set if you wish. Okay, always finite. So, so I have defined the notion of a Markov chain. Sometimes people like to say that this is a one-step Markov chain or one memory Markov chain, because you could think of a Markov chain for which this quantity here, this event here, depends on the most recent 2 random variables, right? So that's called order K or K memory, or I don't know what you like to call it, but it's a higher order Markov chain. But in our discussion, we will only be talking about first order Markov chain. All right. Some people have also talked, some statistics people also call this like ARMA or AR1 process, something like that. Okay. We will only talk about first order Markov chain, which means that the memory is 1. We only remember the most immediate past. Okay. So now any questions? Any questions from the Zoom people? Can you see me? So I defined the notion of Markov chains, and we will have a very long discussion of Markov chains. In particular, we will prove many interesting properties about it. Depending on where we start, we will find out where we end up, okay, with certain probabilities. That is our objective. Does anyone have any questions of the definition of Markov chains? Okay. Otherwise, I want to do a small little exercise, all right? So, example, this is all given in the book. So we consider a discrete time stochastic process, Zn, n greater than 0. And here, each Zn is a finite integer value. I don't even need to say finite. Let's say finite, oh, sorry. Integer valued. This finite may not be necessary. I don't know why I wrote finite. Let's just say integer valued random variable. Okay. But Zn depends on the past m bigger than 1 random variables, i.e. Zn depends on Zn minus 1, Zn minus 2, all the way until Zn minus m. Okay. So we can rewrite this as probability of Zn condition on Zn minus 1 all the way down to 0. Say n is bigger than m here. Okay, otherwise it's not meaningful. Okay, probability that Zn condition on Zn minus 1 all the way up to Zn minus m. Okay, so what this is shorthand for, as you can see here, there are more random variables here because n is bigger than m. Okay, if n is equal to, okay, maybe make m strictly bigger than m. Okay, so there are more random variables here than there are here, right? Okay, strictly more. So what happens here is, what this is saying is that Zn only depends on the, Zn only depends on the past m. If I know the past m random variables, then even if you give me other random variables like Z0, it is useless for me to say anything meaningful about Zn. Okay, so is this a Markov chain? Okay, it's kind of close to a Markov chain. So everyone understands the notation. So I just want to say that here we have, let me just put down. Here we have n minus 1 random variables. Here we only have m random variables. Okay, and say n minus 1 here, n is n, sorry. There are n random variables here. So n is bigger than m, so there are more random variables here. But this equality is saying that if I want to know anything about your health at time n, all I need to know is your health at the last m years. Anything before the last m years, say when you were a baby, does not matter. Okay, so this is the stochastic process that we care about, that we are concerned with at this point in time. So is this a Markov? So the question is this a first order Markov chain? I didn't define what is first order Markov chain, but hopefully you can make up a definition on your own. All right, this is not quite a first order Markov chain. All right, it's an m order Markov chain. Yeah, m is not 1, otherwise it's not interesting. All right, so this is no, because Zn depends on a lot of things. Actually, it depends on m things in total. So it's not quite a first order Markov chain. But can we massage this Markov chain a little bit so that it becomes a first order Markov chain, right? So let us try to make this a first order Markov chain. Let's define Zn minus 1, Zn minus 2, up to Zn minus m. Okay, so basically this guy here is this guy here. All right, this collection of random variables is this. Okay, let's define this as the state. So I expand my state space. State of the process at time n minus 1. And now this state space of this random variable here is Cartesian product Sm, right? Right. If each of the random variables here is integer value and lives on S, say S is the set 1 to m. Okay, So this is Cartesian product as M, all right? The state space is slightly larger. Okay, if we define this as the state of the process, okay, at time n minus 1, then we have the following. Zn minus 1, let me just write this down first. Zn minus m plus 1, condition on Zn minus 1 all the way up to Z0. This is equal to probability of Zn minus 1 all the way down to Zn minus m plus 1, condition on Zn minus 1 all the way down to Zn minus m. Okay, so what am I doing here? You notice that I have some repetitions. Okay, so this part here, look at this part here. This part here is in fact part of this part, right? Part of this. Okay, let me not be so lazy and let me put in one more here. Zn minus m plus 1 and Zm. Okay, so this part is included in this part. So do you agree? Right, you see this? All right, I agree that originally it might be a bit confusing, but now if you look at this part is the replicated part. So once I condition on this part here, I can easily put it here because this part has this is nothing but replication of this. Duplication if you wish. All right, and similarly, you have duplication here as well, right? So that we can always do this, right? Because we are multiplying by 1. All right. Okay. So, right, because this guy here, this collection of random variables is deterministic on this. Is deterministically a function of this. So we can just add random variables here without changing. Since we already know this, we can just insert this. So now, if we define xn minus 1 to be the state at time n minus 1, we define xn minus 1 to be this big random variable, n minus m, okay? Xn minus 1 is given by this for each n. Then the above relation, let's call this star. I already called it star, right? So I need to give it a dagger here. Then dagger reduces to probability. Okay, this is xn, all right, because you notice that this guy here is just an increment. This guy here is nothing but xn. Okay, if you define xn minus 1 to be this, you increment everything by 1, right? And then what do we have here in the remainder? We have xn minus 1. We have actually a lot of replicates here, xm minus 1 here. Okay, so if you take note, okay, let's just look at the last one here. If you replace all the n by m, then the last guy here is exactly equal to 0. Okay, so I just do a bookkeeping of this and I wrote it down here in terms of the x's. And this is nothing but probability that xn is given xn minus 1. Okay, because as you can see here, all the indices here are an increment of all the indices here by 1. So we have this. So if we expand the state space, okay, so remark, by expanding the state space from originally was S to SM, okay, Cartesian products, i.e. considering m tuples of the random variables Zn, all right, we convert the m dependence, the dependence on past m random variables to just the past 1 random variable. Okay, so by defining this, this thing here, when we make this definition, if we define, then the collection of x random variables forms a first order Markov chain. Okay, but I think we need this to start from m, n greater than m, forms a first order Markov chain. Okay. Now we did this to start from M, some bookkeeping here because we didn't define what is negative Z. There's no negative time. Okay. So basically we just extended the state space a little bit and then that served our purpose. Okay. Okay. So what I talk about is slightly deviating away from my handwritten notes, but I think what I talk about is more correct because I'm thinking right now. So any questions about this? So what's happening here is the following. You know, you have Zn minus 1, Zn minus 2. Say m is equal to 2. So Zn is depending on this. Zn minus 4. Zn minus 2 is dependent on Zn minus 3 and Zn minus 4 like this. Okay. So now if I group this together and I call this my xn minus 1 and I call this, right, xn minus 2. So this picture is very ugly, sorry. I do not know how to make it look better, but I hope you get the idea, xn minus 3. Then when I talk about two random variables at once, okay, then this sequence of random variables here, the x random variables, forms a first order Markov chain. All right, this picture is very pathetically drawn, but I hope you get the idea. Okay, yeah, so that Z is a second order Markov chain or second order or two order or whatever like we call it, but the X forms a first order Markov chain. Okay, so in particular, we can also label this here Xn. Okay, right. I think I've talked enough about the definition of Markov chains. Do you have any questions? People at home, any questions? Why don't you want to join our party here? Oh, yeah, exactly. Zjian. Xn is a first order Markov chain, while Zn is an M order Markov chain. All right. So we like to write Xn like this. Okay. That's better. Okay. All right. So now we can actually talk about. Hopefully there are no questions. I think this is just pictorial. It's relatively clear. Okay. So now I want to talk about the graphical representation. Okay. Description of Markov chains using directed graphs. Directed graphs. So there are two types of graphs in the world, at least two. If people study graph theory, will object to having two types of graphs. But for my purposes, there are only two types. One is undirected graphs, like this. Okay, undirected means the edges here have no directions. But in our study and in this topic, we will have to deal with directed graphs. Okay, so let me draw a directed graph representing a certain Markov chain with m equals to 6. So there are 6 states. Okay, this is the graph that I'm going to draw right now. So the 6 states are labeled with the integers as follows: 6 here, 5 here, and 4 here. And the transitions are given by the red probabilities. Okay, so here we have a sort of a cycle, and you will see a lot of interesting behavior. This little graph here can illustrate everything we want to see, all the concepts we want to talk about today. All right, P65, P55. So this is a directed graph because all the edges here have directions. We need to indicate the directions. Okay, and P41. And here the state space is of course 1 to m or 1 to 6. Okay, and as I mentioned already above, Pij denotes the probability that you are currently at state I, but then you ended up in state J. Okay, so that's our notation. Okay, we are very particular about our notation. All right. Pij is not the same as Pji. This is not going to be a symmetric matrix. The first index is where you start. The second index is where you end up. It's very important. And so, what do we have? A property of this Pij matrix. Okay, it is non-negative. They are all probabilities. But the sum over j in S of Pij is equal to 1. Okay, so we have this property. But the more I write, the worse it becomes. Pij. Okay, we have this property, right? Because if you are sitting at a current state, say state 6, you have to go somewhere. You could either stay in state 6 or you're going to go to where? Where can you go to? You cannot go, you cannot stay in state 6. You either go this way or you go that way. So the outgoing arrows probability have to sum up to 1. So in this particular case, P63 plus P65 must add up to 1. If it doesn't, you are wrong. All right, so we have this property here. Then do we have the property that sum of Pij, I in S, this is meant to be I in S, is this equal to 1? Do we have this property? Wrong? It's binary answer. No need wrong. And someone else? At home people, Zoom people? I'm looking at you. Do we have this property? No, we don't in general, okay? We don't, okay? Unless the matrix is called a doubly stochastic matrix. I'll talk about this shortly, okay? We are going to have something called a row stochastic matrix here, okay? But I've not talked about what is a matrix yet, okay? Now I'm going to talk about it. So based on this graph here and the probabilities here, okay, we are going to be able to form a so-called state transition matrix. And the purpose of our study in these 3 lectures is to study the properties of the state transition matrix. Okay, that's the whole study. All right. So one more time, if I'm at state 1, this graph here says that I end up in state 2 with probability P12. I stay in state 1 with probability P11. And that's the only 2 places I can go. So if you look at this graph here, right, there are a few interesting things that you can see already. No, who said no? Someone in the Zoom said no. Someone is not muted. Okay. Anyway, there are what interesting features you can see here. Very interesting graph, you see. Now, if you start at state 4, all right? You start at state 4. Can you go to state 6? You know, impossible, right? No matter how hard you try. And I want to tell you that, okay, no matter where you start, you will end up only in 3 places, 3 possible places, right? You will end up either here and you will oscillate among 2 and 3 and you cannot escape, all right? Or you will end up here and you cannot escape. So can people tell me what is this value, P55? Yes. What is this value here? 1, 1, right? Yeah, right. So once you no matter where you start, look at the graph. There are only a few places you can go to, all right? But in the long run, you will only end up in 3 places, 2, 3, 5. All right, you will get trapped there and you cannot escape, right? So we are studying things like where you will get trapped. And how long do you have to wait before you get trapped? Okay, so these are the questions that we will ask, okay, about Markov chains. All right, so I just want to show you that there are some interesting features here. So this will also lead us to the notion of transient and recurrent states, which we'll talk about later on. So a transient state is one in which you will only spend finite amount of time. So suppose you are here, okay? Suppose you start here. So how much time will you spend here on average? So the amount of time that you spend here is governed by P11, right? This is a geometric random variable. You will leave with probability 1 minus P11. The sum of these 2 guys is 1 minus P11. So you will stay here with probability P11. And then let's say that when you leave, you succeed, all right? So the success probability is 1 minus P11. So on average, you will spend about 1 over 1 minus P11 time here. And then you will escape, right? This is a geometric random variable, correct?
Probably on escaping from state 1 is only P12.
Oh, sorry. P12, yeah, probability. So these two have, sorry, I looked at the direction of this arrow wrongly. I thought it's this way. But these two have to add up to 1, right? These two have to add up to 1. And so this is the number of times, the waiting time that you are in state 1 follows a geometric random variable with this probability. Okay, so the expected waiting time is 1 over this probability. Oh, okay. Waiting time to leave state 1. So if you start at state 1, right, the intuition is that you won't spend too much time. You only spend finite amount of time here. Then very soon you will go to state 2. So this is a transient state. Transient in English means you don't stay too long. You will have to leave sooner or later. Okay, we will define these notions properly. But the point here is that we can form a matrix of transition probabilities. Okay, so in Gallager's book, he writes matrix like this. Okay, P11 to P16, P61 to P66. So that, okay, so there exists a directed arc. Actually, we can just say arc. I don't know why they say directed arc. An arc is a directed edge. Okay, from state I in S to J in S, if and only if Pij is greater than 0. Okay, and what we have here are that these row sums are equal. The sums of all these rows. The sum here. Sum of P1j, j running from 1 to 6 must be equal to 1. Sum 6j must be equal to 1, j running from 1 to 6, and same. So this is a row stochastic matrix. Row stochastic matrix means all the rows sum to 1. Okay. Okay, so we have that this is the row sums of P are all 1. This is a row stochastic matrix. And a row stochastic matrix has a lot of nice properties about its eigenvalues and things like that. Okay, so we'll talk about this later on. So is this representation clear? Okay, is this representation clear to everyone at home? And here, any questions you want to ask? So here, what I've done is I've populated the entire matrix, but in fact, there are a lot of entries here are equal to 0. All right. So for example, P16 is equal to 0 because there's no way for you to take one step to go to 6. All right. So this guy here is equal to 0. Okay.
If we use P11 to P16, isn't it very unnatural?
Why?
Because like say Pij is probability of going from I to J, right?
Mm-hmm.
Then when you take P multiply, when you take it and multiply to your probability of being in each state, it doesn't really make sense. You have to put your vector on the left of the matrix.
Yeah. Whenever we do, yes, exactly. Very good. So remember that I said we have an initial state x0. All right. We have an initial state x0. That is this guy here. And we will have a probability distribution x0 I is the probability that x0 is equal to I. That's our initial state. So we can represent this distribution by a certain vector as well. We always represent distributions as row vectors. And when we do multiplication, we multiply on the left here. Okay. So we won't worry about this at this point in time, but I want to caution that, okay, if we are interested to figure out where we are at next time, okay, suppose our initial probability distribution of x0 is given to us, what is the chance that we go to the next state? What's the chance that we end up in the next state? That is given by, okay, let me just make a remark. If the initial state x0, okay, is governed by, has probability distribution px0j, which is equal to probability x0 equals to j, we can form an initial vector, initial probability vector, px0 1 all the way up to px0m. Row vector. And this is a row vector. Okay. Then x1 what distribution? X1 has distribution. Has what distribution? X1 has distribution governed by this probability vector. Okay. Let me just cut this. X1 has distribution governed by, we multiply on the left, P. So this can multiply. This is a row vector, and this is an m by m. This is an m by m matrix. So you get another row vector, px1, 1, dot, 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 pxn, px1, and this is the convention. Okay, x1 has distribution governed by this, which is equal to this matrix multiplication. Okay, that's the convention. Okay, so it's a bit unnatural, but this is the way it is. Okay, this is the convention in Markov chains. We'll see that this we are jumping the step already, because I'll talk about this in greater detail later on, how we multiply. The next thing I want to talk about is classification of states, okay, which is a big topic. But before we talk about this, we need to talk about various graph theoretic definitions, okay? So this part here is a little bit dry, but we have to get through it. So an n-step walk of a graph, of a directed graph, okay, is an ordering of a string of nodes. I0, I1, all the way up to In, n bigger than 1, in which there's a directed arc from Im to Im plus 1, okay, for each 0 less than m less than n minus 1. So this is a notion of a walk, all right? So a walk can be infinitely long. So this is a walk, okay? So let's see, this is a walk. You can go here, 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 and you can do this loop here. This is the walk. So a walk can be infinitely long, all right? So there can be repetitions in these nodes as well. Okay? There can be repetitions. We allow for that, all right? However, we need another notion. A path is a walk. This notion of walk is very important in graph theory, in which no nodes are repeated. Okay, so how long can a path be? How long can a path be? What is the maximum length of a path? Okay, I already told you that a walk can be infinitely long, can be really, really long. Okay, how long can a path be? Can you construct a graph so that the path is as long as possible? Okay, so this graph here, right? This is called a. So this is 1, 2, 3, m. So this path here is of length m minus 1. This path, the path is this one. And this is the I0, I1 up to n minus 1. Let's call it m minus 1. So this is a length m minus 1 path because there are only m minus 1 arrows here. This is the longest you can go. All right. Otherwise, you will have to repeat. Right? And repeats are not allowed in paths. Okay. So this is the longest path you can have. I think it's easy to see. There's no need to prove anything here. Okay. But a cycle can be slightly longer. A cycle is a walk in which the first and last nodes are equal and no other node is repeated. So a cycle is as follows. Okay, we can reuse this picture here essentially. Okay, and get rid of this, and perhaps we have another arc here. So the red walk, it forms a cycle. All right. So these things here form a cycle. Okay. So just a remark here. A walk can start and end at the same node. No. A path cannot. All right. So the reason is because no nodes are repeated in a path. So you are not allowed to have the path start and end the same node because a path cannot have two nodes that are the same. All right. Right. So in this case here, right, this is the path, and each one of the nodes is this different, right? So this is your I1, I0, I1 up to IM minus 1. Okay. So in this particular cycle here, the cycle is a particular walk in which the first and the last nodes are the same. So this is the IM. I0 is the same as IM, right? Agree? Any questions on these definitions? So as a side remark, the number of nodes, number of steps in a walk can be infinity, okay? But the number of steps in a path is at most m minus 1. And the number of steps in a cycle is at most m. Right? So when do you have a cycle that is that has number of steps exactly equal to m? Now this is a particular picture in which the number of nodes, number of steps in this particular cycle is m. 1, 2, 3, m minus 1, and m. Right? So the number of steps in a path here, 1, 2, all the way up to m minus 1 here. Right? So, yep. Okay. So sometimes you can have a cycle whose total number of steps is less than m. You could have this situation. Okay. You could have. So this is a particular cycle, but you could have this situation as well, right? So here we have 5 nodes, but we have a cycle of length 4, right? So we don't have to have a cycle that consists of all the nodes, right? This is a particular. So what I've indicated here is a particular cycle. This cycle here that only has 4 steps, but the total number of nodes in this graph is 5. Okay, I think this should be straightforward. Okay. So now the next few definitions are really crucial. Okay. A state. I will definitely ask you questions about this. J in S is accessible, that's the definition, from another state, I in S, if there exists a walk from I to J. Okay, we write this as the suggestive notation I to J. Okay, so what this means is that if we are at I, there is a possibility that we can go to J. Okay, that we say that in this case we say that J is accessible from I. And what this notation suggests is that there is a walk from I to J. You can somehow walk from I to J. Sometimes you cannot, you know. Like if you are here, okay, so in this graph here, all right, is there a walk from 6 to 2? Is 2 accessible? So we can ask the question, is 2 accessible from 6? Yes. Right? Yes, this is true. 2 is accessible from 6. So is 6 accessible from 2? No, right? Because you cannot find a walk from 2 to 6. Once you're at 2, you're stuck with your wife 3. There's no way you can marry someone else, right? So once you're here, you're stuck. So there's no way to go here. So this is an example, right? Okay. Right, so let's just cut it out. Yeah. Okay, so we know what's the notion of accessibility. Okay. Any questions about the notion of accessibility? Okay. So in our graph there, 1 is a 3 is accessible from 1. Let us check this. Okay, this is a bit obvious, but I need to drill in the point. So 3 is accessible from 1 because there is a path. Maybe I use this pointer. Okay, 3 is accessible from 1 because there's a way for me to get from 1 to 3 via 2. Okay, so this is true. So now let me write down a few more examples for our graph. Sorry, I have to move up and down. 5 is not accessible from 3. We write it as follows. Okay, so let's see if 5 is accessible from 3. So once we are at 3, we are stuck with our wife or husband, 2. So there's no way to go to 5. Okay, so the next claim is 2 is accessible from 2. Okay, we want to make the claim 2 is accessible from 2. Is it so? Yes, there's a walk from 2 to 2. You walk here and there. In fact, there are infinitely many walks from 2 to 2, right? You can use a 2-step walk and you can use a 4-step walk. You can use a 6-step walk. Every even step walk is okay, right? And finally, 6 is not accessible from 6. 6 is not accessible from 6 because once you're at 6, there's no way of you getting back to 6. All right. So we have all these relations. 2 is accessible from 2, 6 not accessible from 6. Okay. So understand? Okay. So here's a fact that we will prove. All right. Suppose a walk that we index by I0, I1, all the way up to IN exists from node I0 to IN, then P of I0, I1, P of I1, I2, P of I2, I3, all the way up to P of IN minus 1, IN is bigger than 0. Okay. Now this looks obvious, right? All right, this looks obvious, but let's just give a formal proof of it. Okay. So what it's saying is that if such a walk exists from node I0 to IN, then the transition probabilities are all positive. All right. So let us just write down what this means. Okay. The probability. So let me write down this justification here. A short proof. So we are concerned with probability that xn equals to IN conditioned on the fact that x0 is equal to I0. Okay, we are interested in this. So what does a walk exist mean? It means that we can get from I0 to IN via I1, I2, I3, and so on and so forth, right? Okay, so let us use basic probability to decompose this. So this is a sum over I1, I2, all the way up to IN minus 1, all the intermediate ones in Sn minus 1. So that's the Cartesian product. Okay, let me make this look nice. Sn minus 1 of probability of xn equals to IN, xn minus 1 equals to IN minus 1 dot dot dot, x1 equals to I1, condition on x0 equals to I0. Okay, so that's just the law of total probability at work. Okay, so now we can write down, we can decompose this a little bit more explicitly. So now let's look at this monster here. All right, so suppose we only have, so the claim here is that this can be decomposed into the probability that xn is equal to IN, condition on xn minus 1 equals to IN minus 1, multiplied by the probability that xn minus 1 equals to in minus 1 condition on xn minus 2 equals to in minus 2, dot, 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 probability x1 equals to I1, condition on x0 equals to I0. Okay, so why is this so, right? Let me just give a short justification for the case where we have justification for the case where we have x2 equals to I2, comma, x1 equals to I1, condition x0 equals to I0. I'm only going to show this. Okay, then this thing here can be done by induction. All right. So how can we do this? This is probability by base rule. Slowly, we have this is condition on x1 equals to I1, comma, x0 equals to I0. Probability x1 equals to I1, condition x0 equals to I0. Right? This is by base rule. What's next? We can use the first order Markov property, which means that we can throw this away. First order Markov property says that x2 only depends on x1. So after we throw it away, we will recover x2 equals to I2, condition on x1 equals to I1, probability x1 equals to I1, condition on x0 equals to I0. Okay, so this is a short proof for the case we have 3 random variables. Here we have n random variables. So, I mean, it's a matter of bookkeeping. Okay, so now this is a big sum. This is a big sum over a big Cartesian product. But all the terms inside the sum are non-negative. So we can lower bound this by the elements of the walk, by the terms inside the walk. And the terms inside the walk are given by I0, I1 up to In. So this can be lower bounded by just this guy here. I don't want to rewrite this. Okay, this can be lower bounded by this, just one term. Okay, because I can throw away the rest. They are all non-negative. Okay, and this by the fact that we are dealing with homogeneous Markov chains, this is P of In minus 1, In, P of In minus 2 to In minus 1, dot, 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 P of I0 to I1, okay? If such a walk exists, then all these are positive. And all these are positive. If this guy here is positive, means all these terms are positive here. All right, because if any one of them is 0, then this is 0. Now this is positive. A walk exists means all these are positive. So we conclude that all probabilities or transition probabilities, if you want to be pedantic, all probabilities P of Im minus 1 to Im are positive for all m between 1 to n. So this is just some small little bookkeeping, all right? And it is also true that if probability xn equals to in, condition on x0 equals to I0 is bigger than 0, then there exists an n-step walk from I0 in S to In in S, okay? So here, this is where we started off with. Here is where we are at time n. And if there is a positive probability for us to get from I0 to In, 2 states, over time n, then certainly there must be a walk of that particular length. Okay, so this is all just a matter of you understanding the definitions of this and that, right? Of a notion of a walk and connecting them to the transition probabilities. Okay, so we write probability that xn is equal to j, condition on x0 equals to I as Pijn. All right, this is not power. This is not power. All right, Pijn is not the end power of Pij. It's just an index. But the reason why we index it in this way there's a good reason. I don't know when we will say this, maybe the start of next lecture. But this is equal to, and we have not proved this, okay? This is going to be equal to, I take the matrix P, then I power it N, and I look at its ij element. So this power here actually applies to the transition matrix. I take the transition matrix, I take its n power, and I look at its ijth element. Okay, and that's why this notation is suggestive of this notation here. But this is something that we have to prove. In particular, what do we have to prove? We have to prove that, okay, the probability that xn is equal to j, given that x0 equals to I, is the ijth entry in the nth power of the transition matrix. But this should be believable. I will do it for the case n equals to 2. Okay? All right. So this I want to repeat is not the n power, but it refers to the n power of the transition matrix. This is something that is not so trivial. We will try to show this later on. Okay, so basically the summary of this part here is that if there is a walk of length n, then this probability is positive. And similarly, if the walk passes through, I1, I0, I1, I2, all the way up to In, then all the intermediate probabilities must be positive. Okay, that means there must be a way for you to get there. There must be a way for you to get from I0 to In via this particular walk here. Okay? Right. Okay. So let me state some very obvious facts. Okay. If there exists an n-step walk from I to j, and there exists an m-step walk from j to k, right? So if you have walked from I to j in n steps, sorry, I pressed something. If you can walk from I to j in n steps, and you can walk from j to k in m steps, then what can you do? Then if you still have energy left, then there exists an m plus n step walk from I to k, right? Okay, so in particular, this means that Pijn bigger than 0, Pjkm bigger than 0 implies that, so maybe this not implies, i.e. mathematically, Pikn plus m is bigger than 0. Okay, so in other words, if you can go from I to j, and you can go from j to k, regardless of the number of steps, then you can go from I to k. All right. So why is this true? I didn't prove this, but we can prove it quite easily. Okay. And this is almost obvious, but let's see. Probability. So we want to show that we are given that there exists an n-step walk from I to j, then there exists an m-step walk from j to k. Then there exists an m plus n step walk from I to k. Of course, if you look at a picture, you can see what's happening, but let's prove this formally. Okay, so xm plus n equals to k conditional on x0 equals to I. Okay, we want to show that this guy is positive. So we use this, we sum over all possible intermediate states. So that is the probability that xm plus n equals to k, condition on xn is equal to, say, L, probability, I'm running out of space, times probability xn equals to L, condition on x0 equals to I. Okay, that's meant to be L. And here L runs over the state space. Right? This is by Bayes' rule, but it's more than Bayes' rule, okay? Here I have jumped many steps. I've jumped many steps. What have I jumped? I have basically used the Markov property. The Markov property says that I only depend on my immediate past. But this is not quite the immediate past, right? Because this is xm plus n, and this is only xn very far away. But so here, we need to be a little bit more careful, all right? So here, actually, what we should do here is, okay, x0 equals to I. This is absolutely correct by using just Bayes' rule. Now, how can we drop this by using the Markov property? This can be dropped. So condition on the event that xn equals to L, I don't care what is the initial state. So suppose I want to know my health at age 20. There's no information about my health from age. This is my health at age 20, this is age 10, and age 0. This is my m plus n, and this is my n, and this is my 0. Suppose I'm interested to know my health at age 20. I have no information about from 11 to 19. I only have information about 10. Okay? So if I want to know my health at age 20, and I only have information here, then this is as good as it gets in predicting my health at age 20. I don't need to know what's happening here. That is intuition. We need to prove that actually we can drop this. Okay, homework. All right, I'm not going to do this. Okay, so that's the Markov property that we are using. And actually we can lower bound this by the probability that xm plus n equals to k, condition on xn equals to j, probability xn equals to j, condition x0 equals to I. So the reason here is because all the probabilities involved here are non-negative, so we can drop many things. Okay, and I only retain the j in S. But this is exactly equal to Pijn. Oh, no, this is Pjk. This is Pjkm. And this is Pijn. And both these guys were assumed to be positive, so this is positive. All right. So this technique here is just nothing but law of total probability as well as Markov property. Okay, so we are basically using Markov property and law of total probability in a very systematic way. Any questions here? Any questions from the people in the Zoom? Any questions about this fact here? So basically, we have a walk from I to j, then a walk from j to k. There's a walk of I length n plus m from I to k. But we need to prove this. Okay, and the proof is that, okay, you are basically counting all the ways in which you can go from I to k via xn. Okay, xn can take many values. So those values are called L. All right, but then we are lower bounding that by a specific value of xn that we know that we are going to pass through with some positive probability. So I just extract the j here. So each one of these terms here is positive. So the product is positive. Okay, let's just, hopefully it's intuitive. Okay, there's no need to draw pictures. Okay, so let us, if this is clear, let us continue, right, with a bunch of other definitions, then we'll prove some things. Two states, I and j, communicate. And this is denoted as I communicates with j. Okay, if and only if, actually this is a definition, I don't need to do if and only if. If I is j is accessible from I and I is accessible from j. So this is a very nice definition because the notation is also consistent with the condition, right? The condition says j is accessible from I and I is accessible from j. So they are mutually accessible if you wish. All right. And mutually accessible is called communicate. All right. Okay. So fact here, which is hopefully easy to prove. If I communicates with j and j communicates with k, then I communicates with k. Okay, you prove this. Okay. We are not going to do it. This is, so we have to prove two directions, right? We have to prove that k is accessible from I and I is accessible from k. But then we need to make use of these definitions here. We make use of these conditions here, unravel what these mean. Okay? Here, please note that we have to prove this direction and this direction because two states communicate if two conditions hold. So it is necessary to prove this too, even though it is, I mean, it's kind of obvious. Okay. This is really important, the next thing. In order for us to progress, we need to talk about class, right? A class C is a subset of states, is a non-empty subset of states in S such that for all I in C, each state that is not equal to I satisfies. So we will check this definition very carefully. Satisfies J in C if and only if I communicates with J, and J not in C if and only if I does not communicate with J. Okay. Right. So this is the definition, okay, of class. All right. So first and foremost, it is non-empty. You cannot have empty classes. And the defining condition is that how to check whether something is a subset of states, a class or not. You have to check this statement here. Right? So you go to everybody in the perceived class of states. And then you look at everybody else. All right? So this is someone in the class of states. You look at everybody else. All right? And it is in C, so it is a partner of J of I. Okay, if and only if those two communicate. All right? And it is not a partner of I, that means we are not in the same class, if they don't communicate. All right. So this is very apparently very abstract. So I need my example. And I don't want to move up and down, so I will just copy this. Okay. So what are the classes here? Right. So let's do, this is not so easy. Let's do a thought experiment. Okay. So this is our beautiful graph. And let's see, what are the classes here? So the claim 2, 3. Let me write this properly. Let's say C1, 2, 3 forms a class of states. So we have to prove that this forms a class of states. Okay. So we are going to go to everybody in the class. Okay. So how do we show this? Justify this. Let's say I take I equals to 2, all right, in C1. Okay. What's the way to show that this is a class? So you go to everybody else. Okay. Who is everybody else? So 1, 3, 4, 5, 6. All right. We need to adhere to this definition here. For every I in the perceived class, in the conjectured class of states, all right, everybody else must satisfy the correct condition. So 1 is not here, right? But 1 is not 2. So 1 is somebody else. All right, so let's check. 1 is not in the class. So it must not communicate with 2. Okay, so 2 is here, 1 is here. So does 1 communicate with 2? No, because we cannot get from 2 to 1. All right. It's not get from 2 to 1. So 1 does not communicate with 2. So it's not in C1. Correct. Now let's look at 3. Does 3 communicate with 2? Okay. Does 3 communicate? What is the meaning of communicate? That means, okay, 3 communicates with 2. There's a question. That means I can get from 2 to 3 and I can get from 3 to 2. Right? But this is true because I can get from 2 to 3. And I can also get from 3 to 2. So 3 should be in the same family or same class as 2. Okay, so now, actually in principle, we have to check everything. Is 4 in C1? Okay, 4 is somebody else. So now I'm talking about 2. Does 4 communicate with 2? No, because I cannot get from 2 to 4. All right, so 4 is not here, not in C1. 5, 6, same thing. I'm not going to do it already. Okay, so this forms a class of states and I proved it. At least I proved by saying, okay. Any questions on this? Any questions on this claim here? This is really important. I can ask you to prove or to argue why this is a class of states. Why this is a class. And then you can ask, oh, is 2, 3, 5 a class? No, this is illegal. Illegal class. Not allowed. because it doesn't satisfy the definition of class. Okay, so you can ask, right, which are the other classes of states? All right, claim C2 equals to 1 forms another class of states. Another class of states. Note that a class of states is non-empty. All right, this is non-empty. Okay, very good. So now what do we need to check? Any other state must satisfy some property, right? Okay, any other state. So which are the other states? 2, 3, 4, 5, 6. Right? So 2, 3, 4, 5, 6 must not communicate with 1. Okay, let's check. 2 does not communicate 1 because we cannot go, although we can go from 1 to 2, we cannot go backwards. There's no walk from 2 to 1. All right. 3, same thing. 4, 5, 6, same thing. Okay. So you verify this. Okay. And more claims. The other classes are the following. 4, C4 is 5, and C6 is 6. Hey, some numbering is wrong. I cannot count. C5 is 6. So there are 5 classes of states. There are 5 classes altogether. And 4 of those classes are singletons. And 1 class has 2 states. All these need to be shown properly, or at least you need to know why each one of these subsets is a class. Okay? All these you verify. Okay? You need to go back to the definition to verify. There are many things to verify. All right? If I have, how many statements do I have to verify actually? Here, every state, okay, every class here, there are 5 classes. And then for each particular class, we need to sweep through all possible J's. Okay? So this is a claim. You should try to convince yourself it's true. Okay, so now let us try to, this is again another important definition, and one can get very confused about these things. A recurrent state I, okay, is a state, is one that is accessible, and I've talked about what is mean of accessible, from all other states that are accessible from I. Okay, so what this means is the following, okay? Mathematically, it's probably easier, okay? I is recurrent, not current, it's recurrent. I is recurrent, state I is recurrent, means that if I can find a J such that J is accessible from I, this implies that I is accessible from J. That's the meaning of a recurrent state. Accessible from all other states. Okay, I is recurrent means that if I can find someone else that I can travel to, then I can go backwards as well. Okay, so in particular, there is no possibility of going to J from which there is no return. So in particular, if one enters a recurrent state, then what happens? We return to the state eventually with probability 1. Okay. So if we return to that particular state with probability 1, okay, so say we enter a recurrent state, let's call that state I. Then we return to the state I with probability 1. So the picture is as follows. Here is I, and here is some J, okay? There is a way for us to get from I to J, all right? Then there is also a way for us to get from J to I, All right, so something will happen here. Doesn't really matter what happens over here, and something will happen here, right? Maybe here like that. So doesn't really matter what happens to the other side, to the other states here. Okay, something will happen, but there is a way for us to get from no, this, let me just get rid of this first, confusing. Let's just say that there exists a J for which we can get from I to J. All right. And if there exists such a J, I is said to be recurrent if we can get back from J to I. All right. So if there's a way for us to get back to I, all right, what following events will ensue? We will visit, the point here is that we will visit I infinitely often. Okay, now suppose you are now sitting at I. There is some other state J for which there is a possibility for us to get to. And once you are at J, there's a possibility for you to return to I. Okay, so now you restart the whole process. You're at I again. So you can go to J and then you can come back. All right, so you revisit I infinitely often. Okay, so that is the notion of a recurrent state. Okay, that is the notion of recurrent. So definition, a transient state is one that is not recurrent. Okay, so that is the notion of a transient state. Okay, so let's see. I wanted to draw these pictures now, which will confuse the whole world. All right. So suppose we have this situation. Is I transient or recurrent? Let's focus on our beloved I. All right. This is our I. We are here, and we have this graph. Is I transient or recurrent? Transient, yes, because I can find you a state such that you can go there, but you can never come back. And that state is called K. All right. So I can find you a state such that you can travel there, but you can never come back. You will get stuck at K. So in this particular situation, I is transient, right here. But if I get rid of this, okay, then I is certainly recurrent. Because you can go to J. Once you go to J, you can come back. Once you go to J, there is a possibility of you coming back. So you will revisit I infinitely often. Okay. And after the break, now we're going to take a break. We will prove this proposition. State J or I, whatever, is recurrent if and only if sum up to infinity of Pjn is equal to infinity. N equals to 1. So after the break, we will prove this. But for now, we will take a 10-minute break and then we will come back. Okay. Right. So let's take a toilet break. Oh, we have one person in the waiting room. Sorry. Okay, so we come back at 7:33. Okay. Then we'll prove this small little result.
Will there be a PS7 since we're preparing for our business?
Yeah, short one. I will upload it very soon. Yeah.
Right.
Yeah.
This to show that.
Wait. Maybe I should stop the recording first. Sorry. Okay. Thank you for the question. I made up. Usually I just copy the question from somewhere like Gallager's book or my old exam problems. But sometimes I'm in the mood and I come up with new problems that I think are very interesting. As I mentioned, a typical course on stochastic processes will cover martingales, but we don't have time to do that. That is usually stochastic processes 2. but you can be exposed to martingales even in the context of Poisson processes. Okay, so I think you can do that sort of question. All right. So we recall what is the notion of recurrent state. A state is recurrent if a state J is recurrent. Above I use I, all right, but a state J is recurrent if I can get from J to a certain state, and from that certain state I can get back to J. All right. So from this logic here, we want to prove this proposition. All right, and the proof goes as follows: the number of visits to state J for state J, which is recurrent. Okay. If we start from state J, if start from state J, okay, is infinite by the above logic, and thus it has infinite expectation as well. So this is just a small exercise, okay? So let us write this down as follows: in expected number of visits to state J, condition on x0 equals to J is infinity. Okay, so because if I start from state J, my x0 is equal to J, then I'm bound to revisit state J. And once I revisit state J, I can repeat the argument. I will visit state J 2 times, then 3 times. So the expected number of visits to state J, if I start from state J, is going to be infinity. Now I'm going to let in be the random variable given by the following: if xn is equal to J and otherwise. Okay, so what does this random variable mean? N equals to 0. This refers to the total number of visits to state J. Okay, so this in here, actually this is a bit imprecise, but this in here is a conditioned on x0 equals to J. But we always start from x0 equals to J in this proof. Okay, so now let us do the following: expected value of sum of in x0 equals to J up to infinity, n equals to 0. Okay, but in is a non-negative random variable, so this we can apply something called Tonelli's theorem, which I'm never ever going to test you. So we can interchange the expectation and the sum. Okay, so this can be done. Sometimes this cannot be done if these are not well behaved, but here it can be done. All right. So now, what is the meaning of this expectation value of an indicator random variable? That is the probability that xn is equal to J, conditioned on the fact that x0 is equal to J. Right. So because what we are using here is just the fact that xn is equal to J, this takes on the value 1. So this expectation, we are conditioning on this stuff here. We are carrying this conditioning, and this indicator gets converted to the probability that xn is equal to J. Okay, so this indicator variable is actually very powerful. So what do we have here? This from n equals to 0 to infinity. So this is an n step, right? This is we are going. This is an n step walk from J to J. So that's pjj raised to the power n. Okay, so we know that this is equal to infinity. All right, so this is also equal. The right hand side here is also equal to infinity. Okay, so thus the result follows if J is recurrent. Okay, so what if J is transient? So remark. So this ends the proof. Okay. Any questions about this? So the claim here, let's just remind ourselves, is the following. We have a particular state that we know is recurrent. All right. That means that this J is a recurrent. And what does recurrent mean? It means that if we start at state J, I can find some other state that I can walk to, like say I. Okay, so the picture is as follows. So I'm at state I. There's some other state that I am accessible to, say J. And this state J is very special in the sense that there is also another walk to state I. Sorry, this should be J, okay? A bit small. All right. So because there is a walk from state I to J and J to I, so if this is supposed to be J, oh my gosh. Sorry, this proof here focuses on J. This is I. So this is my focus at this point in time, okay? So J is recurrent, means that I can find some other body, some other person there, I, such that I can walk from state J to I. And then from I can get back to J. Okay? So repeating this argument, the expected number of times I visit J is infinity. Okay? And the expected number of times I revisit J is exactly this quantity, because this random variable refers to the total number of visits to J. So the expected number of times I visit is also infinity. So this actually can go inside, okay, something called Tonelli's theorem. And this is an expectation of an indicator, which is a probability of that particular event. Okay. But we give this a notation PJJN. Okay. So hopefully this is clear. Any questions?
Your expectation equals to infinity. That sounds a bit not rigorous. Properly speaking, we should show that like
yeah.
not bounded perhaps.
Yeah, we can do something like the following, right? Greater than L for any L you like, right? For every L, we can say for every L bigger than 0, this is true. Okay, all right. Okay, then at this point here, we can be super rigorous and say that, oh, this is bigger than L. Okay, so you pick.
Expectation doesn't converge.
Okay, we want to be rigorous, say we do the following, okay? The number of visits, if we start from state J, the number of visits to state J is larger than L for any L. Okay, you give me your favorite L, say 100. All right, then the expected number of visits is bigger than 100. Okay, so say L, okay, L. So this is bigger than L. And so what we have shown is that this infinite sum here, so we have shown that the infinite sum PJJN is bigger than L. 0. But this holds for every L bigger than 0. So now we can take L to go to infinity here. That's the proper way of doing things.
As in, for the equality parts,
Where?
since your expectations themselves are infinite, does your Tonelli theorem still hold or what?
Okay, that's independent of this. These equalities here are independent of whatever this thing is. All right, because this thing here what I'm just doing here is basically I'm moving this inside. This is allowed because all the random variables inside here are positive or non-negative. This is allowed. Whatever this is bigger than L. This part here does not matter when I move this expectation inside here. Independent, okay? Independent in the sense of independent arguments, not independent random variables, okay? Right. So this guy here is bigger than L for any L you choose. And then the next argument is that this expectation can go inside. This comes from Tonelli's theorem. Okay, then the rest of the calculations are algebra. And then we arrive at this thing bigger than L. Now we take L to infinity. This is the correct order of doing things if we want to be very rigorous, okay? Yeah, okay. Thank you. Because I know that some people are not comfortable with infinity. I'm also not comfortable. So thanks for keeping me honest. All right. On the other hand, if J is transient, that means it is not recurrent. All right. So every time the Markov chain visits state J, then there's a positive probability. There's a positive probability, say 1 minus FJJ, all right? So FJJ is the probability, we go back to J. Here, FJJ is in 0, 1, okay? That it will never return to J. Okay, so the total number of visits to J is geometric with finite mean 1 over 1 minus fjj, which is finite. Okay, because fjj here is in the open interval 0, 1. Okay, so we have this picture here just now. Okay, so this is a transient state. This one is a transient state. Okay, so the chance that it goes away is by 1 minus fjj. It's here. 1 minus fjj. Okay, so the expected number of times, expected number of visits to 1 is 1 over 1 minus fjj, which is the mean of the geometric random, mean of a certain geometric random variable. Okay, so in this particular case, maybe I can write this as f11 instead, equals to p12. That is the, so 1 here is transient. Okay, now here, as you can see, it is also easy to see that 4 is transient, right? It is not recurrent. Why is it not recurrent? Because I can find you one other state for which I can go to, but I can never return. Say 2. Look at 4. Okay, now we are at 4. Okay, now there is one other state. Let's call it 2, such that we can go there, but we can never return. Okay, what is the expected number of visits to 4 when I start from 4? It is 1 minus p for 4. Right, is 1 minus p for 4, right? So 1 minus p for 4 is the 1 divided by 1 minus p for 4 is the expected number of visits to 4 if I start from 4. Geometric random variable. And we've encountered a lot of geometric random variables in this class. Okay, so this is a major theorem. The next one. Okay, so in a finite state Markov chain, we talk about class. We talk about recurrence. We talk about transients. Now we are going to put all these concepts together. This is a major theorem. Right? In a finite state Markov chain, either all states in a class are transient or all are recurrent. So now we have to fully understand 3 definitions together: class, transient, recurrent. So what this is saying is that if you have a class is a subset of states. You cannot have some people inside that are transient and some people that are recurrent. Either everybody is recurrent or everybody is transient. Okay, that is a theorem. And it is a bit non-trivial. So one more time, we have understood the notion of class. Hopefully you have understood the notion of class. All right? And we'll revisit that in the proof. Hopefully you understand the notion of recurrent and you understand the notion of transient. And the fact of the matter here is that if you have a class, you have a bunch of states inside that class. Maybe 5 states. All right? Everybody, if one guy there is transient, every guy there is transient. If one guy there is recurrent, everybody is recurrent. This is the theorem. And this is not so trivial. Okay, this requires a proper proof. So this is the first non-trivial thing that we will prove today. All right? Proof. Okay. So let I be transient. What does it mean? So we will unravel all these definitions. So i.e., there exists a J such that I can get from I to J, but I cannot get back. Okay, so I highlight this transient and this meaning here. The meaning here is that there exists a J such that I is such that I can get from I to J, but I cannot come back. This is the meaning of transient. First, we write down the definition in the IE. Okay. Now, suppose I and K are in the same class. Say class C. What do we want to prove? What would we like to prove now? We would like to prove that K is transient. It cannot be recurrent if we want to prove the theorem, right? Because I and K are in the same class, if I tell you that I is transient, you must tell me that K is transient according to the theorem. Okay? So suppose I and K are in the same class. Okay? Then what does this mean? Okay? This means that I communicates with K. That's the meaning of I and K are in the same class. Okay. Okay, so this basically now we need to unravel the definitions properly. This in the same class means this. Okay, so I highlight transient means the green thing. I and K in the same class means the, I guess this orange thing. Okay. So what do we have here? So we have combining all the relations. We have that K, I is accessible from K, and I and J is accessible from I. So why is this so? We are just using 1/2 of this to construct this, and we are using this to construct this, right? But now by a previous fact, okay, we can write so. So what? K, J. J is accessible from K because we can concatenate these two walks together. All right. Okay, so this is just in preparation. I will draw a picture later on. Now, if to the contrary, that means we are preparing to use contradiction. If J to K, all right, what does this mean? Now, if to the contrary, K is accessible from J, the walk from J to K can be extended to I. All right. So if we have this condition here, okay, if to the contrary, K is accessible from J, then the walk from J to K can be extended to I. Why? Because we have this. So we already have this. Then the walk from J to K can be extended all the way to I because we have this also, right? This, however, contradicts the fact that I is transient, or I is not accessible from J. Okay? Thus, there is no walk from J to K. Okay, so what we are trying to contradict is this statement here. Now, if to the contrary, K is accessible from J, all right, then the walk from J to K, which is this notion here, the walk from J to K can be extended to I. So we can actually go from J to I because I is accessible from K. Okay, I is accessible from K. So we can create this entire new walk. Now, however, this would contradict the fact that this will contradict the fact that I is not accessible from J because I is transient. Okay, thus we know that this statement here is not true. All right, thus there is no walk from J to K, which means that K is not accessible from J. Hence, K is transient. Why? Because I can find a node J such that J is accessible from K, but I cannot go backwards. Okay. Okay. So let me repeat this argument. It's kind of important. So here the picture is as follows, okay? Let me draw a small little picture. This is I and this is K. And I and K are in the same class. This class is called C. Okay? Now, let I be a transient state. Okay? Let I be a transient state. What does that mean? This means that there exists another state J such that I can go to J, which means J is accessible from I, but I cannot go backwards. Perhaps there is a self loop here and I cannot go backwards. So I is transient. Okay? Now, suppose I and K are in the same class. So that's what I drew here. They are in the same class, class C. Now, what does this mean? This means that I and K communicate. All right? So, if to the contrary, right, J can talk to K, so K is accessible from J, then the walk, suppose K is accessible from J. So suppose we have this. Sorry, how do I get rid of this?
It's forgotten. It's forgotten.
So suppose, okay, let me get rid of this. All right. So suppose to the contrary, there exists this path or this walk from J to K. All right. Then the walk from J to K can be extended to I here, as you can see. All right. Now, this, however, contradicts the fact that J does not have a walk to I. Okay. You cannot go from J to I because I was assumed to be transient initially. Okay. Thus, there is no walk from J to K. All right. Hence, K itself is transient because I can find a J such that I can get to J from K, but I cannot go backwards. All right. So this is just a small little argument to string all our definitions together. Okay. So, hence, all states in a class are transient. If any state in the class is, if any of them are. Okay, so everybody is transient. And from this little proof here, we can also say that, all right, all states in a class are either recurrent or transient, or either all recurrent or transient. Okay, we didn't really prove the recurrent part, but it should be obvious, or you can construct this on your own. All right. Anyway, it's obvious that if everybody is transient, you cannot have any guy that's recurrent, right? Because you cannot have a state that is both recurrent and transient. And we have already proved that if any one state is transient, then all the other states must be. Okay. So we are basically constructing this by contradiction. If we can look at this particular J, okay, we want to show that K is transient. But if we assume this, then the walk from J to K can be extended to I. This, however, contradicts the fact that we cannot get to I from J because of the transience of I. Thus, there is no walk from J to K. Hence, K is transient because for the particular K, I can find you a J such that K can go towards J, but you cannot go backwards, which is exactly this picture here. Okay. So K and I are in the same class. I is transient because there is a J here such that I can get there, but I can never go backwards. But I and J are in the same class, so I can repeat the argument for K. And in particular, if there is a walk from J to K, then I can extend this towards I. So I have this long walk towards I. But then this will contradict the fact that I is transient. So I've said this like 3 times. Okay? Yeah.
I think there's a break in the argument where you say, now if to the contrary, you can get to K from J.
Yeah.
You never say that you can't get to K from J.
Oh, okay. So we want to show now. Maybe maybe this line is a bit confusing. Okay. Now if let's just get rid of to the contrary. If you can construct this, if you can believe this argument, let's say we can write down that K is accessible from J. Okay. Let's just say we can write down this argument. Let's just say we can make this statement. Then the rest of this will follow, right? But then this will contradict the fact that I is transient. So this statement must be false. All right. Maybe to the contrary is not that well written, and it confuse some people because I haven't said what is contradicting. Okay. But this statement will do is enough. Then this statement must be wrong. All right. So we must have that K is transient itself because I was assumed to be transient. Okay, so maybe we can just eliminate this if it's confusing. Okay, so now let me give you a concrete example. Okay, I don't know why it's called the gambler's ruin, but it's called the gambler's ruin example. Okay, so here our state space is 0, 1, 2, 3. We have 4 states. And we are as follows. 1, 2, 3. 0.4, 0.4, 0.6. This is 1 and 0.6. Oh, I know why it's called gambler's ruin. Because we can make $3. Suppose we start anywhere. So we start with $1. We need to be really lucky to be able to make $3, right? Because it seems that at least if you're a normal person, you will lose all your money from this graph, right? You will get absorbed into 0. But sometimes you may be super lucky and you get absorbed into $3 and you stay there, right? So that's called a gambler's ruin, okay? So here we have the following state transition matrix. Okay, we can write down this state transition matrix as follows. So this is a 4x4 matrix. You always need to check that it's row stochastic. So this guy here is not column stochastic. It is row stochastic. So all rows should add up to 1. And the way I've written this, all rows add up to 1. So we must check that this is row stochastic and this is not column stochastic. This doesn't add up to 1. Okay. But there are some Markov chains that are both row and column stochastic. Those are called doubly stochastic matrices. Then we can prove more things about it. Okay. Then you will have an exercise on that. So what are the classes here? So the claim here is that we have 3 classes. Class 1 is 0. Class 2 is 1, 2. And class 3 is the single state 3. Okay. So these are our classes. Let us try to verify at least a few things. Okay, let us try to show or argue that class 1 is, that 0 forms 1 class. Okay, so this is another exercise in trying to figure out what are classes. What is the definition of class? So the claim is that 0 itself singleton forms a class. First, we need to check that it's non-empty. Okay, it's not-empty, of course. All right. Then we need to check everybody else. So these are the everybody else. Okay. So what is the criterion that 2 nodes are in the same class? That means they must communicate. All right. But 0 does not communicate with anybody here. So it forms a class on its own. Now 3 also does not communicate with all these people here. So 3 is a class on its own. Okay. So we need to verify that this forms a class now, this subset. Okay. That's not so obvious. Let's look at 1. Okay. Look at 1. Look at everybody else. In particular, now we focus our attention on 1. Okay? Focus on this thing here. And then we look at everybody. We look at this. Does it communicate with 1? No, because you cannot get back. Does this communicate with 1? No, you cannot get back. Does this communicate with 1? Yes, you can go there and you can get back. So 1 and 2 form a class. Okay, so that's the proof. Right? Hopefully you understand my speech. Okay, and I don't have to write down all this. But you should convince yourself that all these are the correct classes. No less, no more. Okay. Now let us check something else. Okay, so this claim you verify again. Okay. Okay. So now let us check the following. Let's look at class C2, which is it's the most interesting class because it has several states. Oh, it's very cold here. I cannot write. All right, 1, 2 here. Let's check this. So theorem says that all states in a class are either all transient or all recurrent. So let's go to this picture here. 1. Is 1 transient or recurrent? Transient. Okay, I don't need to check 2. It is also transient. Okay, because the theorem says so. Okay. Now, if you look at 2 carefully, then it's also transient. It's not recurrent. All right. So this is transient and this is transient. All right. So this is just a simple example of a transient class. Now, because we have proved this theorem that says that all states in a class are either all recurrent or all transient, we can refer to classes as transient or recurrent. Now, if you have a mixture of states that are transient and recurrent inside a class, then you cannot really say that the class is transient or recurrent. All right. But because all states in a class are homogeneous, either all transient or recurrent, so this is a transient class. We can say this. Okay. And it's also easy to check that C1 and C3 are recurrent classes because the states contained therein are recurrent. So we can make use of this terminology. Okay, does that make sense? Because we have a priori, we have proved that theorem. We have proved that theorem. Okay. Any questions about this example? Any questions about this example? Oh, we have one question from Zijian. I don't know when. Do you understand this question? State 6 cannot translate from. So means.
Previous example. State 6 only has 1 arrow coming out, right?
State 6 has 2 arrows coming out, right?
Yeah, state 6 is not really.
I knew now. State 6 is transient. Yes, now you know. Good. 6 is transient. Yeah. From in this example.
Wait, 6 doesn't communicate with 6.
By definition, the definition for class.
The definition 6 is a class on its own. This is a class, right? Because you check everybody else. Okay, you check this guy here, this guy here, this guy here. So you cannot get back. It doesn't. 6 does not communicate with anybody else. Okay. You look at this definition very, very carefully. Every state j not equal to I. You only need to check other people. You shouldn't check 6, right? You shouldn't check 6. Every j not equal to I. Look at this. Right? You only check other people. You don't check yourself. Understand? So 6 is a class on its own. To answer Zijian's question. Understand?
How about class 5? I mean class 4.
Okay, so claim is that 4 forms a class on its own. Prove it, okay? So what do we have to check? We have to check everybody else, all right? Does it communicate with J? Can it communicate with 4? Does it communicate with 4? Can we get, okay, we can certainly get from 4 to 1. Can we get back to 4? No. Because one, you will travel here after a finite amount of time, and then you'll get stuck here in this recurrent class. Okay, so 4 does not marry 1. 4 does not marry 2. 4 does not marry 3 either. Okay, 5. We can certainly get from 4 to 5, but we cannot get back. All right, so 5 does not communicate with 4. Agree?
I was asking the class 4. So that means
I'm doing class 4. Yeah.
Note 5.
I'm doing class 4. Yeah.
No,
What?
the note 5. Note 5.
Okay, no, you want me to do note 5, is it? Okay. 5, let's claim that 5 is a class on its own. Okay, so what do we need to check? We need to check everybody else, right? Okay. So, okay, oh, there's nothing to check. Because you see, let's check everybody else. Let's check 4, 6, 2, 3. Does 5 communicate with anybody? No, cannot. Yeah. Does 5 communicate with anybody? No, it doesn't. Right? It doesn't communicate with anybody. So 5 is a class on its own. You need to check other people because look at the definition here. Each state J not equals to I satisfies J in C if we communicate, or J not in C if we don't communicate. You only need to check those that are not I reiterate. Okay. So if we are concerned with 5, right, then we need to check whether 4 communicates with 5 or not. It does not. 1 does not communicate with 5 either. Communicate means go both ways. You can go there, you can come back. Okay. Is this clear? This should be super clear. 子健 clear or not? 子健? Okay. I don't know. Okay, good. All right. So where's the? Is this clear to you? Okay. So I mean, if you're not clear about this, you can ask me over email or office hours. This is really important. Okay. The final concept that we want to talk about is not so trivial also. All right. It's actually a bit confusing. All right. The first time you see it, the more times you see it, the more it's clear to you. Definition. So if you look at our favorite Markov chain here, you will see that if you get trapped here, right, then you visit 2 after you visit 3, and so on and so forth. So you can think of visiting 2 at every even time, 3 at every odd time, something like that. Okay. So there is some periodicity here, period. All right, there's some period here. So we want to make this precise. Okay. Definition. The period of a state I in S denoted as di is the GCD. You know GCD? Greatest common divisor. This is important. Of those values, of those integers, and maybe n is better, for which PIIN greater than 0. Okay, so in particular, DI is equal to GCD of those n's such that PII is greater than 0. Okay, I will illustrate this with a bunch of examples, of course. If the period of a state I, DI, is equal to 1, if the period of state I, DI is equal to 1, then I is aperiodic. Otherwise, it is periodic. Otherwise, it's periodic with period DI. Okay? So that's the definition. the period of a particular state. So sometimes you could have periodic states, sometimes you could have aperiodic states. All right, so we need a bunch of examples to be able to grasp this concept. I will provide 2 examples, and I can guarantee you in the exam, I will ask you for the period of something. Okay, so now we have got this beautiful Markov chain. If you look at my previous exams, I'll ask you what is the period, because it's very easy to grade. If you tell me the period is 3 and the answer is 2, you're obviously wrong. Very easy to be deterministic. I don't have to read your proof, right? Okay, so what this Markov chain and all the arrows indicate positive probabilities, okay? What's the period of node I? Okay, let's just work with I equals to 1. This is symmetrical, right? So we just have to work with I equals to 1 and answer everything. Okay, so let's figure out P11. P11 is actually 0, right? But P112, is it 0 or not 0? It's not 0, right? Because there is a walk of length 2 to vector 1, this walk, right? So this is positive. Oh, let me do this. Okay, how about P113? Is it 0 or greater than 0? P113. Odd. 0. Very good. So I'm not going to put down the 0 one. So okay, P114. 4. Can we get back? If we start at 1, can we get back to 1 in 4 steps? Yeah. P115 is 0. 6 is greater than 0. It's easy to see. Right? So the ends, so the what is this thing here? So what are we trying to do? So we are interested in the D1, the period of 1 is equal to the GCD of all ends such that P11n is bigger than 0. Okay, but it should be clearly obvious that these ends are those ends such that n is even. Right, from the consideration that we had here. Right, it should be obvious the way I drew the Markov chain. So what's the greatest common divisor of even numbers? 2, right? 2 is the biggest divisor of all those even numbers. This is easy example. The next example is not so easy. Okay. So any questions about this example? Okay, so now let me show you a more interesting example. This was I think previous exam. Then you really have to understand the definition. And these definitions are useful because the point of this whole chapter is to understand the behavior of Markov chains. And if you have Markov chains that don't satisfy some conditions, they have radically different behaviors from other Markov chains. Okay. So this example looks very funny. Oh, 2 circle shapes, 2 cycle shapes. D1. Okay, the claim here that's not so obvious, right? Is that all the Ds are the same. All the periods of all the nodes, all the 9 nodes here are the same. So this does not have so much symmetry already, right? Okay. But let's just figure out D1 and D2 to D9 is your exercise. Okay. So let's figure out D1. Okay. P11. Can we get to 1 in 1 step? No. Can we get to 1 in 2 steps? No. Get 1 in 3 steps? No. Can we get to 1 in 4 steps? Yes. Because we have this walk here. 4-step walk. Now, can we get to 1 in 5 steps? No. 6 steps? No. 7? No. 8? Yes. Okay. Seems reasonable. Okay. But if we're not careful, we stop here. Right? The GCD of these 2 numbers is 4. Then it's not quite correct, right? Because I only took care of this part here, right? It's not enough. So 9, how about 9? I think it's 0. But you need to do bookkeeping and check that's not 0. You need to do counting. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9 are not enough. Right? We cannot get back to 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. Not enough. All right. But 10. I think it's enough. This is positive. Why? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can get back to 1. Okay, so it should be easy to see that P1112 is also greater than 0 because we make 3 small loops. Okay, and so on. You see that you can never do odd numbers. Odd numbers will always be 0. Okay, so what is the G? This D is the GCD of these numbers 4, 8, 10, 12, and so on and so forth. This is 2. The period is 2. So if you are very lazy and you only check these 2, you would conclude that the GCD is 4, but it cannot be 4, right? Because you have to take into account this chain also here. So this is another example to illustrate GCD, to illustrate the period. Okay, any questions on this? So, exercise. Check that DI is equal to 2 for all I, 1 to 9. Okay. So unfortunately, this lecture, right, this class here is a bit dry because I need to go through all the definitions before we can do some interesting calculations. Any questions on this example? And this example, I think the first example is easy. The second example is not so easy. You need to actually manually calculate, right? Any questions at all? I only have one more big proof to do. And one more example to do. Okay, if not, let's do another example. All right, and this is the gambler's Rubin example. Okay, so just to drill home the point of period. Yeah, this is so stupid. So I have this particular example here. I want to figure out the period. Okay, so now we know a priori that this is a particular class. 1, 2 is a class. I just showed it last time. I argued that 1, 2 forms a class. Okay, what is the period of 1? Okay, what is the period of 1? So we have to check, right? Is the GCD of those n such that P11n is bigger than 0? So can we get from 1 to 1 in one step? No. So this set here is 2. We can get from 1 to 1 in 2 steps. Here. We can get from 1 to 1 in 4 steps, and so on and so forth. Or even numbers. So the GCD is 2. By the same logic, I'm not going to do this. The GCD of this, the period of 2 is also 2. So these 2 states here, these 2 states here form a class. They form a class C, and their period is 2, right? Both these states have the same period. And a very natural question now for the good student. Just now we proved that everybody in the same class is either all transient or all recurrent. Here we have the situation that these 2 people in the same class, 1 and 2, have the same period. Could you have a situation where you have 2 states in the same class? One has period 5 and one has period 17. So this is the last theorem. That is a bit surprising also, the first time you see it. Okay, for any finite state Markov chain, I'll just write Markov chain. All states in the same class have the same period. Okay, so this is not a coincidence, right? Everything I do has a purpose. This example now is not a coincidence that 1 and 2 have the same period. It comes from a theorem that says that if both of you are in the same class, you must have the same period. 2 or 3 or so on and so forth. All right, so now let's do another example before we prove this. Okay. So this example, what are the classes? What are the classes? How many classes are there and who are the people in each class? There's one class and everybody is in the same class, right? Thank you, thank you, thank you. And we showed that D1 is 2. By symmetry, everyone is 2. This is symmetrical, right? So this does not violate our theorem. Nice, right? Okay. So here, how many classes are there? It's not so simple, right? You need to think about what is the definition of class. Now, I asked you to do an exercise just now. Prove this back home. Okay? But first and foremost, let me ask you a question. How many classes are there here? And what are the people in each class? One class, yes. So everybody is in the same class. We did a very hard work to show that we did hard work here to show that D1 is 2. Equipped with the next theorem that we are about to prove, you don't have to do this. Because everybody has the same period. Because upstairs, someone there just said that everybody is in the same class. We showed that D1 is 2. So everybody must have period 2. Make sense? Yeah, we don't have to do this exercise once we prove that theorem. The last theorem here. Okay? All right, so this theorem here requires you to know something that is, the proof in the book is too fast. It's way too fast. This is theorem 4.2.8. And in my notes, lecture 7, okay, I showed something that's really required, okay? And I'll show you why I think the proof in the book is not correct. And this is after accumulating a bit of teaching experience for this class. Okay, every year I come to this point and I don't like this proof in the book. Most of it is fine, but they are missing out one point that I will elaborate on. And I have 33 minutes to elaborate on. This is the last thing I want to do, so I'll do it slowly. Okay. Everyone understands the statement of the theorem. You need to know what's class, you need to know what's period. All right. Okay, so let I and J be a pair of states in the same class. In the same class. Say C. Okay, so this implies that I communicates with J. So I communicate with J. What does it mean? Actually, this is if and only if. Okay. This implies that there exists two integers n and m in N, such that Pijn greater than 0, Pjin greater than 0. M. Okay, that's what I meant to do. Pjim. Picture is as follows. Okay, I is here, J is here. You take an n step walk here, and you take an m step walk here. Okay, there exist such walks. All right. So, since there exists a walk of length n from I to j, and there exists a walk of length m from j to I, we prove a theorem just now, or fact just now, that says that there exists a walk of length n plus m from I to I via j. Of course, right? This is obvious, right? Sorry, this is not so obvious if you do the wrong thing. Here, n, you can walk from I to m using n plus m steps, obviously, right? So this is, I don't even write this down, okay? So this implies that di, which is the period of node I, right? The period of node I divides n plus m, okay? So this means that n plus m is divisible by di. Other n plus m, same thing, n plus m is a multiple of di. Di is the greatest common divisor. Di is the greatest, is defined to be, recall, to be the GCD of those, say, n, all right, such that pii n bigger than 0. It's the GCD, all right? And we know that there exists such a walk from I to I of this length, okay? So it must be true that di divides this, n plus m. Okay. So now what we are going to do is we are going to artificially create this walk here, okay, of length t. We're going to artificially create this, but let me write this down properly, okay? Let t be any integer such that pjjt is bigger than 0, okay? Any integer such that pjjt is bigger than 0. Why? Why does such a t exist? Does t exist? You have to ask this question. Why? Why does such a t exist? Yes, exactly. Right? Because we can go to I and go to j. So t, at least one t exists, m plus m, right? Right? At least one such t exists. Yes. But this t is arbitrary, all right? Such a t exists, but at this point of the proof, it is arbitrary. Okay? So what do we have here? Clearly, there is a walk of length n plus m plus t from I to I. Now, how do you get from I to I in n plus m plus t steps? You can go from I to j, and then j to j, and then j to I. N plus m plus t, or n plus t plus m, whatever. Okay, so by the same logic as we had here, right? Di divides n plus m. So di also divides n plus m plus t. Artificially insert this t, right? By the same logic, here there was a walk of length n. Here there was a walk of length n plus m. Di is a divisor of n plus m. Here we artificially inserted this red walk t, right? So di is also certainly divisible by n plus t, right? Artificially inserted. Now, if you have this together with, okay, if we have now di n plus m and di n plus m plus t, we have these two statements here. What can you deduce? Di divides t, right? So if you do not know this, so we can write down explicitly. This implies that di is equal to some k di is equal to n plus m, where k is integer, right? Here, the second statement means that n plus m plus t is equal to k, sorry, you must have L, right? L di. L is bigger than k, at least k, right? So this means that L minus k di is equal to t. So t divides di, right? So this is some number thing. It's not number theory, but it's a number thing. Number logic, right? If I have these two statements, then clearly d must divide t. But and the proof is here. All right. If this extra part must be a multiple of di. There's no other choice. All right. Now, so this is true for every t such that pjjt is bigger than 0. Because we fix t here, let t be any integer such that pjjt is bigger than 0. Okay? This is true for every t such that pjjt is bigger than 0. Okay? So this means that di divides dj. This is the non-trivial step. Okay? This is not highly non-trivial, but this follows from a fact that is not explained in the book. Okay, so here's a fact. All right. Let m and n be two integers such that their greatest common divisor is equal to d. Okay. Then, if a is any common divisor of m and n, then a also divides d. Okay, this is not so trivial. This requires a big proof. Not big proof, but it requires a proof. So now this guy here is the greatest common divisor. Okay, remember that dj is defined to be the greatest common divisor of those t such that pj jt bigger than 0. Okay, so what we are making use of is this fact here, that di divides every t such that pjjt is bigger than 0. It also divides the greatest common divisor, right? So this is exactly using this fact here, but this fact requires a proof. Okay, it actually is not so obvious to me. Okay. A is any common divisor. A is a common divisor of both m and n. Then A also divides d. So we have this result here in the box. Okay. But there is nothing special about I and j in this order. Flip the rows of I and j. This implies that we have dj also divides di. We can repeat this whole argument with I and j interchange. So now we have these two boxes, right? If you divide me and I divide you, we must be the same. So this implies that di is equal to dj. And I and j were from the same class. So this completes the proof. Okay. So this is not so clean, it's not very beautiful proof, but then it is not so trivial. So I want to repeat myself, okay? So the claim is that all the states in the same class have the same period. All right. And I showed you a few examples just now to show you that this theorem is not violated. Okay. To show you that the theorem is not violated. At least for the examples that we have seen, the Markov chains that we have seen, all the nodes, all the states in the same class indeed have the same period. That's the first thing to check. Whether we have any counter examples in life or not. All right. We don't, at least not yet. Okay, so we are going to try to prove this carefully. So let I and j be a pair of states in the same class. All right. So where are we using the fact that they are in the same class? Where are we using the fact? We are using a fact right here in this picture. Okay. They are in the same class, means they communicate. This means that there exists a pair of integers, n and m, such that we can go from I to j in n steps, and we can go from j to I in m steps. This picture here. Okay. Now this line here is obvious. There is a walk of length n plus m here. Right, from I to I. So di clearly divides n plus m because di is the greatest common divisor of those numbers such that pii n is bigger than 0. Okay, recall that di is equal to the GCD of those numbers, say L, such that PIIL is bigger than 0. So it's the greatest common divisor of those numbers. So certainly di divides n plus m. Okay. So this is just the notation. This is the notation for this is a multiple of this. Okay. So now we are going to artificially create this. All right. So t is any integer such that pjjt is bigger than 0. All right. So there is a walk of now a longer length from I to I. How do we get this? Go here, here, here. And this is a walk of length n plus m plus t. All right. So we have this situation, this statement here. Now, once we have this and this, we know that di is divisible by t. But this t is arbitrary. And in particular, this t is some t for which pjjt is bigger than 0. Okay. This is how we chose this t. Okay, at the beginning. What is not so obvious, and we need a particular fact that is in red, is the following. If we have a bunch of numbers, here I only write down 2 numbers. Okay. If we have a bunch of numbers such that their GCD is equal to D, and A is a common divisor of these 2 numbers, then A also divides the greatest common divisor. I think here we need to use something called Bézout's identity or something like that. Okay. So now all these T's, right, are analogous to these objects here. Here we have M and N. Here we have a bunch of T's. And DJ is the greatest common divisor of those T's such that pjjt is bigger than 0. Okay. Now, DI is a particular common divisor of all those, of this M and N, which is analogous to a common divisor of all those T's such that pjjt is bigger than 0. All right. So we have this is divisible by the greatest common divisor. Okay. So when we apply this fact here, how do we apply the fact? Okay, we apply the fact by M and N here is analogous to all those T's such that pjjt bigger than 0. Okay. A is analogous to DI. And D is analogous to DJ. Okay, that's how we apply the fact. Okay, you just check. Of course, if you are a good student, all right, you will notice that this fact is not enough. Why is this fact not enough? We need actually a slightly stronger fact. Because here we could have infinitely many T's. Here I only have 2 M and N. So here we could have many T's here, but here I only have M and N. So this fact here is strictly not enough, but it's believable. All right? You see the issue here? Yeah. So here I relate M and N, this set here to this set here. It's not quite correct, right? But it's good enough, I think. We could generalize this fact a little bit, but never mind. It's too difficult to write. So we have DI divides DJ after using this fact. This fact is not mentioned in the book. All right. Then flip the rows of I and J, we have this other relation. And so these two are the same. So the punchline here is the following. Remark. We can, the conclusion from today's lecture is that, the conclusion is that we can say, we are allowed to say, class C is transient. We can say this. We're allowed to say this because everybody in the same class has the same transience or recurrence behavior. So if one person is transient, everybody is transient. Okay. We are also allowed to say, we can say that class C is recurrent. Okay, we are allowed to say this. And what are we also allowed to say now? Oh man. We are also allowed to say that class C has period D. Okay, because everybody has the same period. All right, you cannot have period 2 and have period 3 if we are friends. This is what we proved today. This is the punchline. Okay. Right, the rest next week. Okay. So today we introduce a lot of different notions, and you will have to play with these notions in a limited problem set. Do you want 3 problems or 4 problems? I think 3 is fine. I will readjust. All right. And you have to do those and to familiarize yourself with the definitions. It's not difficult. I asked you to do the first 2 problems of Gallager's book in this chapter. Cannot be too difficult. Okay. So I will send out a proper announcement about the quiz, but roughly speaking, or not roughly speaking, precisely speaking, quiz 2. Today is what date? 5th, is it? 5th, right? Quiz 2, 12 March. Everyone needs to show up as usual. Up in person. Except we have one person stuck in India. We will zoom invigilate that person. Okay? Everyone needs to show up in person. LT1 starts from 6 p.m. And because someone requested we start from 6 p.m., I'm very nice. Start from 6 p.m. to 7 p.m. 1 sheet of paper. And you don't need me to tell you that it is on Poisson processes. Okay? Any other details that I missed out? Oh, now you don't need to bring paper. You write on the paper. I realized that I don't like to collect your paper. Some people give me big paper, some people give me small paper. So you write on the paper. I realized that that's better. Okay? But you can bring extra paper for working. Okay? 1 sheet of paper, you can write on both sides anything. Okay? And I think it's not so difficult. Any questions about the quiz?
How many tips on the quiz?
What tips? I always give you tips, right? Right. I said that, oh, I will ask you a question about what is the period of this and what is the period of that. All right. I always drop tips here and there. I cannot remember what tips I gave for Poisson processes, but I always drop tips here and there. I tell you one. I mentioned this last lecture. I will examine you. I can even write this down. There's nothing to hide. I will examine you on conditional arrivals. I can even tell you what is conditional arrivals. You have S1 to Sn, condition on the fact that Nt is equal to N. This has the same distribution as something, okay? Yeah. So this, we prove this sort of thing, right? This has the same distribution as something, the order statistics of something, all right? So you should try to, well, this is my tip. Any more? You want any more? It's okay. Since it's told to everybody, it's okay. Yeah. I cannot tell a subset of people, right? Yeah. All right, so these are the details. Did I miss out anything? I've already designed everything. I've already written the solutions. Yeah. All right. If not, we end 10 minutes early and have a very, very good weekend. Please submit the current homework and the next one will be short. Okay. Thank you. See you. Bye-bye. Yeah. Yes, thank you very much. I forgot. Otherwise, I will get a scolding. Huh? Yeah, here it is. And I guess I have to take a picture of your beautiful selves. So this side smile. Just spread out. This side, smile. Okay, thank you very much. And thanks for reminding me about this. Did anyone forget to take temperature? Oh, some people did. These people forgot to take temperature. Zhao Yuxuan and Muhammad Yosef asked me, please do this, okay? And thank you. Oh, okay. The rest can leave, okay? If you have taken your temperature. Thank you. See you. Bye-bye. Any questions, feel free to ask. So wait. I want to stop the recording. Hello. Bye-bye. Bye, people. How do we stop? Do we just stop everything? Okay. Bye-bye.